Welcome back to the channel where we explore the universe's deepest mysteries. Today, I'm going to tell you something that will completely shatter your understanding of reality. You know how we've always been told that nothing can escape a black hole? Not even light, the fastest thing in the universe? Well, here's the thing that physicists have known for decades, but rarely explain properly. Gravity isn't actually escaping the black hole at all. In fact, what we call gravity coming from a black hole isn't even a force in the traditional sense. The black hole isn't pushing or pulling anything. Instead, it's doing something far more profound and mind-bending. It's literally changing the shape of space and time itself, and that warping was already there before anything fell in. The gravity you feel from a black hole is just you responding to the twisted geometry of space-time that the black hole's mass created. But here's what will really blow your mind. If you could somehow instantly delete a black hole from existence, the gravitational effects wouldn't disappear instantly. They would ripple outward at exactly the speed of light. So gravity is limited by light speed, but it doesn't need to escape because it's not inside in the first place. It's the arena itself, the very fabric of reality, that's been bent. Are you confused yet? Good, because by the end of this video, you're going to understand something that most people never grasp. The true nature of gravity, why Einstein called it the happiest thought of his life, and why black holes are actually the universe's way of showing us that space and time are not what we think they are. Before we dive deeper, do me a favor. Hit that like button right now and subscribe if you haven't already. I need to know who's watching this from where. Drop a comment telling me what country you're in and what time it is for you right now. I'm genuinely curious if you're watching this at 3 in the morning, unable to sleep because you're thinking about the universe, or if you're procrastinating on something you should be doing. Either way, I see you and I appreciate you being here. Let's start with what you think you know. You've probably heard that black holes have such strong gravity that nothing can escape them, not even light. This is true, but it's also deeply misleading in a way that causes massive confusion. When you hear this, your brain probably pictures something like a cosmic vacuum cleaner, sucking everything in with an incredibly powerful force. You imagine light trying desperately to escape, pushing outward with all its energy, but the black hole's gravitational force is just too strong, pulling it back down. This is how almost everyone visualizes it, and it's completely wrong. Not just a little wrong fundamentally, conceptually wrong in a way that misses the entire point of what Einstein discovered. Here's the first thing you need to understand. In Einstein's theory of general relativity, which is our best description of gravity, gravity isn't a force at all. I know you've spent your entire life thinking about gravity as a force. Newton told us it was a force. Your physics teacher told you it was a force. Every diagram you've ever seen shows gravity as an arrow pulling things together. But Einstein proved that this is just an approximation, a useful fiction that works well enough at low speeds and weak gravitational fields, but misses the deeper truth. Gravity is actually the curvature of space-time itself. Now, I can already hear you saying, okay, but what does that actually mean? Let me give you an analogy that actually works, not the oversimplified trampoline analogy you've probably seen 1,000 times. Think of it like this. Imagine you're an ant crawling on the surface of a balloon. As far as you're concerned, you're walking on a flat surface, going in straight lines. But now someone starts inflating the balloon unevenly, creating bumps and valleys. You keep walking in what feels like a straight line to you, but an observer from outside can see that you're actually following a curved path, going around the bumps and into the valleys. You don't feel any force pushing or pulling you. You're just walking straight ahead like you always do. The curvature of the surface you're on is what determines your path. This is what mass does to space-time. Massive objects don't pull on other objects. They curve the fabric of space-time, and objects moving through that curved space-time follow curved paths. When you see an apple fall from a tree, the apple isn't being pulled by Earth's gravitational force. The apple is actually moving in a straight line through curved spacetime. And that straight line through curved space just happens to intersect with the ground. Einstein figured this out in 1907, and he later called it the happiest thought of his life. He was sitting in his office at the patent office in Bern, Switzerland, when he realized that if a person falls freely, they don't feel their own weight. Imagine you're in an elevator and the cable snaps. As you fall, before you hit the ground and your life flashes before your eyes, you would be weightless. You could let go of your phone and it would float next to you, not because there's no gravity, but because you and your phone are both falling at the same rate. From your perspective inside the elevator, it's as if gravity has disappeared. Einstein realized this meant that gravity and acceleration are two sides of the same coin, and that what we call gravitational force is really just the experience of being accelerated through curved spacetime. But here's where it gets interesting for our black hole question. When a massive star collapses into a black hole, it doesn't suddenly create new gravity. The gravity, or more accurately, the spacetime curvature, was already there. If our sun suddenly collapsed into a black hole right now, which it won't, because it's not massive enough, but if it did, Earth would continue orbiting exactly as it does now. We wouldn't get sucked in. The gravitational field at Earth's distance would be identical. The black hole would have the same mass as the sun, so it would curve spacetime in the same way at the same distance. The only difference would be that now there would be a region close to the black hole, inside what we call the event horizon, where the spacetime curvature becomes so extreme that all paths through spacetime lead inward. This is the key insight. The event horizon isn't a physical barrier. It's not a membrane or a surface made of anything. It's a point of no return in spacetime geometry. Once you cross it, every direction you can move in time leads you toward the singularity at the center. Not because something is pulling you, but because the geometry of spacetime itself has become so warped that outward no longer exists as a direction you can travel in time. Now here's what's truly mind-bending. The information about the black hole's mass, the curvature of spacetime it creates, exists in the spacetime around the black hole, not inside it. When you're outside a black hole and you feel its gravitational effects, you're not detecting something coming from inside the event horizon. You're responding to the curved geometry of spacetime that the black hole's mass created. That geometry extends throughout space. Think of it like the surface of a trampoline again, but better. Once you put a bowling ball in the center, the entire surface is curved. You don't need information to continuously travel from the bowling ball to the edges to maintain that curvature. The curvature just is. It's a property of the geometry itself. But wait, you might say, doesn't this violate causality? If something falls into a black hole and increases its mass, doesn't the outside universe need to somehow know about this mass increase? Doesn't information need to escape from the black hole to tell the universe to curve a little bit more? This is an excellent question, and it brings us to one of the most subtle and beautiful aspects of general relativity. The answer is that the increased curvature propagates outward from the event horizon as a gravitational wave, traveling at the speed of light. The information doesn't come from inside the black hole, it comes from the event horizon itself, from the disturbance in spacetime geometry at the boundary. When two black holes merge, we can detect the gravitational waves from that merger, as we famously did for the first time on September 14, 2015, at the LIGO Observatory. That detection, announced in February 2016, was led by scientists including Rainer Weiss, Kip Thorne, and Barry Barish, who later won the Nobel Prize in 2017. Those gravitational waves carried information about the masses and spins of the black holes. But that information came from the dynamics of spacetime geometry during the merger, not from inside either event horizon. Let me make this even more concrete with a thought experiment. Imagine you're floating in space, watching a massive star collapse into a black hole. As the star collapses, its surface gets smaller and smaller, but its mass stays the same. At every moment during the collapse, the gravitational field you experience at your location doesn't change, because the total mass hasn't changed, and you're staying at the same distance from the center of mass. When the star's surface finally shrinks below its event horizon and the black hole forms, still nothing changes for you. The space-time curvature at your location was created by the mass of the star, and now it's maintained by the mass of the black hole. But from your perspective, the gravitational field is identical. The event horizon isn't emitting gravity or sending out gravitational force. It's just the boundary where space-time curvature becomes extreme enough that return is impossible. Here's another way to think about it. Gravity isn't a thing that travels or escapes. It's not like light, which is made of particles called photons that move through space. Gravity is a property of space-time geometry. Asking why gravity can escape a black hole is like asking why the shape of a bowl can escape from the ball. The question doesn't quite make sense, because the shape isn't something separate from the bowl, it is the bowl. Similarly, the gravitational field isn't something separate from spacetime, it is the curvature of spacetime. But now I need to complicate this picture, because, as always in physics, the truth is more nuanced. While gravity isn't a force that propagates from inside the black hole, changes in the gravitational field do propagate, and they propagate at exactly the speed of light. If you could somehow magically make a black hole vanish instantly, which you can't, but let's pretend the gravitational effects wouldn't disappear instantly throughout the universe. Instead, the change would ripple outward as a gravitational wave at light speed. Observers far away would continue to experience the black hole's gravitational field until the wave reached them, at which point they would suddenly find themselves in flat spacetime. This is exactly analogous to what would happen if you could make the sun instantly disappear. We would continue to see sunlight for 8 minutes, the time it takes light to travel from the sun to Earth, and we would continue to orbit the sun's location for those same 8 minutes, until the information about the sun's disappearance reached us via gravitational waves. This reveals something profound. While gravity isn't a force propagating from inside the black hole, gravitational information is still limited by the speed of light. General relativity is what we call a local field theory. This means that what happens at one point in spacetime can only influence what happens at another point through continuous propagation between them, and that propagation can never exceed the speed of light. So in a sense, gravity does respect the same cosmic speed limit as light. But it doesn't need to escape from inside the event horizon because it was never inside in the first place. Are you starting to see the shift in perspective that's required here? We're not talking about gravity as a thing that exists and moves around. We're talking about the dynamic geometry of spacetime itself. The black hole is a region of spacetime. The gravitational field is the curvature of spacetime, and the propagation of gravitational changes is a wave in the curvature of spacetime. It's all spacetime, all the way down. Now, let me take you even deeper. One of the most confusing aspects of this whole discussion is understanding what we even mean by inside and outside a black hole. We tend to think of the event horizon as a spatial boundary, like the surface of a planet, but it's not. It's actually a boundary in spacetime, which means it's a boundary in both space and time. This is going to sound wild, but inside the event horizon, the roles of space and time are actually swapped in a certain mathematical sense. Outside a black hole, you can stay at a fixed distance from the center. If you accelerate outward, you can hover in place. But once you cross the event horizon, moving toward the singularity isn't a choice anymore. It's as inevitable as moving forward in time as for us right now. You can no more avoid reaching the singularity than you can avoid reaching next Tuesday. This is why light can't escape. It's not that light doesn't have enough energy or speed. Light always moves at the speed of light. That's the one constant in the universe. But inside the event horizon, all light cones, all possible futures, point toward the singularity. There is literally no direction in space-time that light can travel that leads outward. It would be like trying to travel backward in time. The geometry simply doesn't allow it. And here's what's really going to bake your noodle. From the perspective of someone falling into a black hole, they would cross the event horizon in a finite amount of their own time, probably not even noticing the moment they crossed it for a sufficiently large black hole. But from the perspective of someone watching from outside, they would never quite see the infalling person cross the event horizon. They would see them slow down, getting dimmer and redder, asymptotically approaching the horizon, but never quite reaching it. This isn't an optical illusion. It's a consequence of how space-time is structured near an event horizon. The infalling person's time becomes infinitely dilated relative to the outside observer's time as they approach the horizon. Both perspectives are equally valid, and this apparent paradox is resolved only when you understand that simultaneity, the concept of two events happening at the same time, is relative and breaks down completely in extreme gravitational fields. So when we talk about gravity escaping from a black hole, we're really asking a malformed question based on Newtonian intuitions. The black hole doesn't emit gravity. The black hole is a region of space-time with extreme curvature, and that curvature extends throughout space-time. The curvature at any point outside the event horizon was established by the matter that collapsed to form the black hole before it crossed the event horizon. Once established, that curvature persists because space-time has inertia, in a sense. The geometry doesn't just snap back to being flat when matter crosses the horizon. It remains curved, and that curvature is what we experience as gravity. Let me pause here and let that sink in for a moment. We've just established that gravity isn't escaping from black holes because it was never inside them to begin with. The gravitational field is a property of space-time geometry that exists everywhere, not a signal being transmitted from inside the event horizon. But this leads us to an even deeper question. If gravity is just curved space-time, what is space-time? Is it a thing? Does it exist in some fundamental sense? Or is it just a useful mathematical description? And what does it mean for something massless like a photon of light to be affected by space-time curvature? After all, Einstein's other great theory, special relativity, tells us that photons don't experience time. From a photon's perspective, if it had one, it would be emitted and absorbed in the same instant. So how can a photon follow a curved path through space-time if it doesn't experience time? And here's the real kicker that we're going to explore. Quantum mechanics tells us that particles can be in multiple places at once, in superposition. So what happens to space-time curve? What if I told you that everything I've just explained to you, this entire picture of gravity as curved space-time, might only be an approximation? That it works brilliantly for black holes, planets, stars, and galaxies, but that at the deepest level, gravity might actually be something else entirely? Stay tuned, because we're about to enter the realm where general relativity and quantum mechanics collide, and where physicists are still trying to figure out what the hell is really going on. Welcome to the section where we start to pull back the curtain on what gravity really is, and it's going to require us to think about reality in a completely different way. You've probably noticed that I keep using this phrase, curved space-time, as if space-time is some kind of thing, some kind of substance that can be bent and stretched. But what is it actually? Is space-time real, or is it just a mathematical abstraction, a convenient way of organizing our calculations? This question leads us into one of the deepest debates in physics, and the answer has profound implications for understanding black holes, gravity, and the nature of reality itself. Let's start with a bit of history. Before Einstein, space and time were thought to be absolute. Isaac Newton, back in the 1600s, believed that space was like an infinite container, just sitting there, providing a stage on which the universe plays out. Time, similarly, was absolute. It ticked away at the same rate everywhere in the universe, regardless of what was happening. In this view, Space and time were just coordinates, labels we put on events with no physical reality of their own. Gravity, in Newton's picture, was a force that acted instantaneously across space. If the sun were to suddenly disappear, Earth would immediately fly off on a tangent, no delay. Einstein shattered this picture. In his 1905 theory of special relativity, he showed that space and time are not separate, absolute things. They're interwoven into a single four-dimensional fabric called spacetime. Different observers moving at different speeds will disagree about measurements of space and time. What's simultaneous for one observer isn't simultaneous for another. Lengths contract, time dilates, but they'll all agree on the structure of spacetime itself. Then, in 1915, Einstein completed general relativity, showing that this spacetime fabric isn't just a passive stage, it's dynamic. It can bend, flex, and ripple. Mass and energy curve spacetime, and the curvature of spacetime tells objects how to move. But here's the question that physicists have been arguing about for over a century. Is spacetime a real, physical thing, or is it just a mathematical model? This might seem like a philosophical question, but it has real consequences for how we think about black holes and gravity. There are basically three positions you can take, and brilliant physicists have defended all of them. The first position, called substantivalism, says that spacetime is real. It's not made of atoms or particles, but it's a genuine thing that exists, has properties, and can be bent and warped. In this view, when we talk about curved spacetime near a black hole, we're talking about something that really exists out there in the universe. The curvature isn't just a mathematical description. It's an actual feature of a real entity called spacetime. Kip Thorne, one of the pioneers of black hole physics and one of the co-founders of LIGO, tends toward this view. He talks about spacetime almost like it's a physical medium, and his work on things like wormholes and time travel treats spacetime as a genuine substance that can be manipulated. The second position, called relationism, says that spacetime is not a thing in itself. Rather, it's just a convenient way of describing the relationships between physical objects and events. In this view, what's real are the object's particles, fields, whatever, and the distances and time intervals between them. Spacetime is just the mathematical framework we use to organize all these relationships. The curvature of spacetime, then, isn't a thing that exists, it's shorthand for saying that objects move in certain regular patterns. This view goes back to Gottfried Leibniz, who argued with Newton about the nature of space in the 1700s, and it's been defended more recently by physicists like Carlo Rovelli, one of the founders of loop quantum gravity. The third position is sort of in between. It says that spacetime might be an emergent phenomenon, something that arises from more fundamental constituents at smaller scales, the way temperature emerges from the motion of molecules. In this view, at the scales we can observe, spacetime is real enough. It has definite properties and follows definite laws. But at the Planck scale, which is about 10 to the power of minus 35 meters, space-time might dissolve into something more fundamental, like a network of quantum information or relationships between quantum states. This is the view suggested by many approaches to quantum gravity, including string theory and some interpretations of loop quantum gravity. Here's why this matters for our black hole question. If space-time is a real, physical thing, if substantivalism is true, then the curvature near a black hole is a genuine feature of reality. The event horizon is a real structure in spacetime, even if it's not made of matter. The singularity at the center is a place where spacetime itself becomes infinitely curved and perhaps ceases to exist in any recognizable form. In this picture, gravity is fundamentally about the properties of spacetime, and asking whether gravity escapes from a black hole is like asking whether the shape of a mountain escapes from the mountain. But if spacetime is not a real thing, if relationism or emergence is true, then the picture changes. The curvature near a black hole is just a description of how test particles would move if you placed them there. The event horizon isn't a thing. It's a boundary in your mathematical description. And gravity isn't about space-time at all. It's about the relationships between objects, or about whatever fundamental constituents underlie space-time. In this view, asking whether gravity escapes from a black hole is asking about how information propagates between these fundamental constituents, and the answer might be very different from what general relativity suggests. Now, you might think this is all just philosophy, that it doesn't matter for practical physics. But it absolutely does, especially when we start thinking about quantum mechanics. Here's why. Quantum mechanics is all about discrete chunks, quanta. Light comes in discrete packets, called photons. Energy comes in discrete levels. Even things like angular momentum come in discrete units. So if space-time is real, if it's a physical thing, then we might expect that at some level, it too is quantized. It comes in discrete chunks. This would mean that space-time isn't infinitely smooth. At small enough scales, there would be a granular structure, like pixels on a screen. This is exactly what some approaches to quantum gravity, like loop quantum gravity, predict. They suggest that space is made of tiny loops, and area and volume come in minimum sizes. You can't have a region of space smaller than a certain size, just like you can't have half a photon. But here's where it gets mind-bending. If space-time is quantized, then the singularity at the center of a black hole might not actually be a singularity at all. In general relativity, the singularity is a point of infinite density and infinite space-time curvature. But if space-time is quantized, if it's made of discrete chunks, then there's a limit to how much it can curve. As matter collapses, instead of forming a singularity, it might form something called a Planck star, an incredibly dense but finite object held up by quantum pressure. In 2014, physicists Carlo Rovelli and Francesca Vidotto proposed this idea. They showed that in loop quantum gravity, the collapse of matter inside a black hole could bounce back due to quantum effects, potentially leading to a white hole eruption in the far future. This is speculative, but it shows how our understanding of black holes depends critically on whether space-time is real and what its fundamental nature is. Now let's connect this back to gravity and the question of escape. In general relativity, gravity is the curvature of space-time, and it doesn't need to escape from a black hole because it's a property of the space-time geometry that exists everywhere. But in a quantum theory of gravity, gravity might be carried by particles, just like electromagnetism is carried by photons. These hypothetical particles are called gravitons, and they would be quantum fluctuations in the fabric of space-time itself. If gravitons exist, then gravity is transmitted by the exchange of these particles. And now we can ask a more precise question. Can gravitons escape from inside a black hole's event horizon? The answer, according to our current understanding, is still no. Gravitons, like photons, would travel at the speed of light, and nothing traveling at light speed can escape from inside an event horizon. But here's the crucial point. The gravitational field outside the black hole wouldn't be maintained by gravitons escaping from inside. Instead, it would be maintained by gravitons that were always outside, or by gravitons produced at or just outside the event horizon through quantum effects. The black hole's mass curves spacetime, and quantum fluctuations in this curved spacetime produce virtual gravitons that mediate the gravitational force. These gravitons never need to cross the event horizon from inside to outside. Let me give you an analogy. Imagine a pond with a whirlpool. The whirlpool has a point of no return once water crosses it. It spirals inevitably toward the center. Now imagine that the water is made of molecules, and that waves on the surface of the pond are vibrations in the arrangement of these molecules. The whirlpool itself, the overall pattern of water flow, is established by the molecules throughout the pond, not just by the molecules at the center. If you're on the outer edge of the pond and you see waves, those waves are carried by the molecules near you. They don't need to come from the center of the whirlpool. Similarly, Gravitons mediating the gravitational field around a black hole don't need to come from inside the event horizon. They're excitations in the space-time geometry that exists outside. But this raises a profound question. If space-time can have quantum fluctuations, if it's subject to the uncertainty principle, what happens to the very notion of an event horizon? In quantum mechanics, nothing is perfectly defined. A particle doesn't have a definite position until you measure it. It exists in a superposition of positions. So does a black hole have a perfectly defined event horizon? Or is the event horizon itself fuzzy, existing in a superposition of slightly different locations? This is not just a theoretical curiosity. It has real implications, especially for something called Hawking radiation, which we're going to dive into shortly. Before we get there, let me hit you with another mind-bending fact. In 1995, physicist Ted Jacobson showed something remarkable. You can derive Einstein's equations of general relativity from the laws of thermodynamics and quantum mechanics. This is huge. It suggests that gravity, space-time curvature, isn't fundamental. Instead, it's emergent, arising from the statistical behavior of microscopic quantum degrees of freedom, the way temperature arises from molecular motion. In this view, asking whether gravity can escape from a black hole is like asking whether temperature can escape from a hot object. Temperature isn't a thing that escapes. It's a statistical property of the object's constituent particles. And heat transfer is just the exchange of energy between particles. Similarly, gravity might be a statistical property of spacetime's quantum constituents, and gravitational effects would be the result of quantum information exchange. Jacobson's work built on earlier ideas from Jacob Bekenstein and Stephen Hawking about black hole thermodynamics. In the early 1970s, Bekenstein realized that black holes have entropy, a measure of disorder or hidden information. He proposed that the entropy of a black hole is proportional to the area of its event horizon, not its volume. This was bizarre because usually entropy is proportional to volume, like the number of molecules in a gas. But for black holes, it's proportional to area, as if all the information about what fell into the black hole is somehow encoded on its two-dimensional surface. This is called the holographic principle, and it's one of the deepest ideas in modern physics. It suggests that the three-dimensional reality we experience might actually be a projection of information encoded on a two-dimensional surface, like a hologram. If this is true, if the universe is holographic, then the question of whether gravity escapes from a black hole takes on yet another meaning. The black hole's event horizon is like a screen on which information is written. The gravitational field we observe outside is the three-dimensional projection of this two-dimensional information. Nothing needs to escape because the gravity we experience is just us reading the information on the screen. This is still highly speculative, but it's being actively researched by some of the brightest minds in physics, including Juan Naldacena, who discovered the AD-SCFT correspondence. Here's how Hawking radiation works. Quantum mechanics tells us that empty space isn't really empty. It's filled with what we call quantum vacuum fluctuations. Particle-antiparticle pairs are constantly popping into existence and then annihilating each other almost immediately. These are called virtual particles, and they exist for such a short time that they don't violate conservation of energy, thanks to Heisenberg's uncertainty principle. Normally, these fluctuations don't have any observable effect because the particle and antiparticle quickly find each other and disappear. But near the event horizon of a black hole, something dramatic can happen. Imagine a virtual particle-antiparticle pair forms just outside the event horizon. Before they can annihilate, one of them falls across the event horizon while the other escapes. A particle that escapes is real radiation that can be detected far away from the black hole. The particle that fell in has negative energy relative to an outside observer, which might sound weird, but it's a consequence of how energy is defined in curved spacetime. The net effect is that the black hole loses mass equal to the energy of the escaping particle. Over time, as more and more particles escape, the black hole gradually evaporates. Now, let me be clear about something crucial. This explanation using virtual particles is a heuristic, a simplified picture that captures the essence of what's happening, but isn't quite the full story. The real calculation that Hawking did is more abstract. He looked at quantum field theory in curved spacetime, how quantum fields behave when spacetime is curved by a black hole, and he found that the vacuum state, far from the black hole, looks like a thermal state with a definite temperature when observed from outside. This temperature, called the Hawking temperature, is inversely proportional to the black hole's mass. For a solar mass black hole, the temperature is about 60 billionths of a Kelvin, far colder than the cosmic microwave background, which means solar mass black holes are actually absorbing more radiation than they emit. But for tiny black holes, the temperature can be enormous, and they would evaporate rapidly. Here's what's important for our question about escape. Hawking radiation doesn't come from inside the event horizon. It's produced by quantum processes just outside the horizon, in the region we call the near-horizon region. The curved spacetime near the horizon affects the quantum vacuum in such a way that particles are created. One of these particles escapes to infinity, carrying away energy, while the other falls in. So in a very real sense, the black hole is losing mass through a quantum process at its boundary, not through something escaping from inside. But this raises a paradox, one of the most famous in all of physics, called the black hole information paradox. Here's the problem. Quantum mechanics says that information cannot be destroyed. If you know the exact quantum state of a system at one time, you can in principle calculate its state at any other time, forward or backward. Information is conserved. But Hawking radiation appears to be thermal completely random, carrying no information about what fell into the black hole. If a black hole evaporates completely, turning into random thermal radiation, then information about everything that fell in every book, every person, every bit of data would be destroyed. This directly contradicts the fundamental principles of quantum mechanics. Hawking himself initially believed that information was indeed destroyed, that black holes created a genuine exception to quantum mechanics. This view was controversial from the start. In 1997, Stephen Hawking and Kip Thorne made a bet with John Preskill, another physicist, about whether information was lost in black holes. Hawking and Thorne bet that it was lost, while Preskill bet that it wasn't. The stakes were an encyclopedia of the winner's choice, from which information can be recovered at will, a cheeky reference to the information paradox itself. For decades, physicists have been trying to resolve this paradox, and it remains one of the driving forces behind research in quantum gravity. There are several proposed solutions, and they all have profound implications for our understanding of space-time, black holes, and reality. One possibility is that information isn't destroyed, it's encoded in the Hawking radiation, but in such a subtle way that we haven't figured out how to decode it yet. This would mean that Hawking radiation isn't truly thermal. It only appears thermal if you look at it coarsely. There are correlations between the particles that escape, and these correlations encode information about what fell in. This is the view that has gained the most traction in recent years, especially through work on the ADS-CFT correspondence and the firewall paradox. In 2004, Hawking conceded the bet to Preskill, admitting that information probably is preserved, though the mechanism remains unclear. Another possibility, more radical, is that the event horizon isn't quite what we think it is. In 2012, a group of physicists including Am Delhairy, Donald Merolf, Joseph Polchinski, and James Sully proposed something called the firewall paradox. They argued that if information is preserved in Hawking radiation, then the event horizon can't be an innocuous place. Instead, there must be a firewall, a region of incredibly high energy right at the horizon that would incinerate anything trying to cross it. This contradicts general relativity's prediction that you shouldn't notice anything special when crossing the horizon of a large black hole. The firewall idea suggests that either quantum mechanics, general relativity, or our understanding of how information works must be modified. A third possibility, championed by Leonard Susskind and others, involves the holographic principle and something called black hole complementarity. The idea is that information doesn't need to escape from inside the black hole because it was never really inside in the first place. Remember that holographic principle I mentioned? If all the information about what falls into a black hole is encoded on the event horizon, then from an outside perspective, nothing ever really crosses the horizon. It gets smeared out on the surface. From the infalling observer's perspective, they do cross smoothly and fall in. Both perspectives are valid, but they can never be compared directly because no one can cross the horizon and come back to tell you about it. Information is simultaneously inside for the infaller and outside, encoded on the horizon for external observers. And there's no paradox because these descriptions apply to different reference frames that can never communicate. Now, here's where it gets even weirder. Recent work on quantum entanglement and black holes has suggested that spacetime itself might emerge from quantum entanglement. In 2013, Juan Maldacena and Leonard Susskind proposed a radical idea called E equals EPR, which connects Einstein-Rosen bridges, wormholes, with Einstein-Podolsky-Rosen pairs, quantum entanglement. The idea is that when two particles are quantum entangled, when their properties are correlated in ways that can't be explained by classical physics, they're actually connected by a tiny wormhole through spacetime. If this is true, then spacetime geometry is built from quantum entanglement. The fabric of space is woven from quantum correlations. This has profound implications for black holes. It suggests that the interior of a black hole might be connected to the Hawking radiation through quantum entanglement. The particles that fall in and the radiation that comes out are entangled, and this entanglement is the mechanism by which information is preserved. The black hole's interior and its radiation are two sides of the same quantum state, connected through the geometry of spacetime itself. In this view, asking whether information escapes from a black hole is like asking whether the left side of an entangled pair escapes from the right side. They're not separate things that need to escape from each other. They're aspects of a single quantum system. Let me connect this to something you could almost visualize. Imagine you have a long rope that's been twisted into a braid. The left end and the right end of the rope look separate, but they're connected through the structure of the braid. Now imagine that this rope is a wormhole, and the twist in the braid represents quantum entanglement. The left end is a particle that fell into a black hole, and the right end is a particle in the Hawking radiation. They seem separate, but they're connected through the quantum geometry of spacetime. Information doesn't need to travel from one to the other, because they're already connected. This is the essence of A equals EPR, and if it's correct, it means that spacetime, entanglement, and information are all deeply interconnected in ways we're only beginning to understand. But let me tell you why this matters, beyond just solving abstract paradoxes. The information paradox isn't just an academic curiosity. It goes to the heart of what's real and what happens to reality at extremes. If information can be destroyed, then the universe is fundamentally unpredictable. The past doesn't uniquely determine the future. This would overturn not just quantum mechanics, but our entire framework for understanding cause and effect. It would mean that at some level, physics gives up, and we can't predict what will happen next. That's not just philosophically troubling. It would undermine the entire scientific enterprise. On the other hand, if information is preserved, then we need to understand the mechanism, and that mechanism will likely reveal new physics. It might tell us about the quantum structure of spacetime, about how gravity works at the smallest scales, about whether there are extra dimensions, or strings, or something else entirely making up reality. The resolution of the information paradox could be the key that unlocks quantum gravity, the theory that unifies general relativity and quantum mechanics. And here's something that should blow your mind. We might actually be able to test some of these ideas. Not with large black holes. Those take longer than the current age of the universe to evaporate through Hawking radiation. But potentially with microscopic black holes, if we can ever create them in particle accelerators or detect them from cosmic ray collisions. If the Large Hadron Collider or future colliders can reach high enough energies, and if certain theories about extra dimensions are correct, they might produce tiny black holes that evaporate almost instantly in a burst of Hawking radiation. By studying that radiation, we could test whether information is preserved, whether firewalls exist, whether the holographic principle is correct. This would be experimental evidence about the nature of spacetime itself. Now, let me circle back to our original question with all this context. Why can gravity escape from a black hole if light cannot? First, gravity doesn't escape. The gravitational field is established by the mass energy of the black hole and exists throughout spacetime, maintained by the curvature that was set up during the black hole's formation. Second, changes in the gravitational field propagate at light speed, not faster, so gravity respects the same cosmic speed limit as light. Third, in a quantum picture, gravitons that mediate gravity are produced in the curved spacetime outside the horizon, not inside, so they don't need to escape. Fourth, if the holographic principle is correct, all the information about the black hole is encoded on its surface. So the gravity we observe is really us interacting with this two-dimensional information screen. But there's a deeper answer that encompasses all of these. The reason gravity doesn't need to escape is that the question assumes a separation between inside and outside, between the black hole and the rest of the universe that doesn't actually exist at the deepest level. The black hole is not a separate object sitting in space. It is space, or more precisely, it's a region of spacetime with extreme curvature. The gravitational field is not something the black hole produces and sends out. It's the structure of spacetime itself. And if spacetime emerges from quantum entanglement, then the black hole, its horizon, and the external universe are all entangled aspects of a single quantum state. There is no inside and outside in any absolute sense. There are just different regions of an interconnected quantum geometry. This is where physics stands today, on the edge of a revolution in our understanding of space, time, and gravity. We have general relativity, which treats space-time as a smooth, continuous fabric and works brilliantly for everything from GPS satellites to gravitational wave detectors to predicting the orbits of planets. We have quantum mechanics, which treats reality as discrete and probabilistic and works brilliantly for everything from computer chips to lasers to chemistry. But these two theories are mathematically incompatible at the extremes. At the center of a black hole, where both quantum effects and strong gravity are important, both theories break down. We need quantum gravity, a theory that unifies them, and we don't have it yet. But we're making progress. String theory, loop quantum gravity, asymptotic safety, causal set theory, amplitude-hedron geometry. There are multiple approaches, and they're starting to make concrete predictions that might be testable. The discovery of gravitational waves by LIGO has opened a new window into extreme gravity. Future gravitational wave detectors, both ground-based and space-based, like the planned LISA mission, will be able to observe black holes in unprecedented detail. We might be able to test whether event horizons exist or whether they're replaced by something else. We might be able to measure quantum effects in strong gravitational fields. The question of why gravity can escape from a black hole, once you really dig into it, leads you to the frontier of human knowledge, to questions about the nature of reality that we're still actively figuring out. And that's beautiful. That's what makes physics exciting. We don't have all the answers. We might not even be asking all the right questions yet, but we're making progress. One discovery at a time, one experiment at a time, one insight at a time. And every person who thinks deeply about these questions, who lets themselves be confused and amazed by the universe, is participating in this grand adventure of understanding. So where does that leave us? We've established that gravity doesn't escape from black holes because it was never trapped inside them. But we've also seen that this simple answer opens up layers upon layers of deeper questions about the nature of spacetime, the fate of information, and the fundamental structure of reality. And now I want to take you somewhere even stranger, because there's an aspect of black holes we haven't touched on yet, something that connects directly to your everyday experience in a way you might never have imagined. We're going to talk about time, specifically about how black holes reveal that time is not what you think it is, and how this relates to your subjective experience of the present moment. Because if you think the stuff about gravity was mind-bending, wait until you see what black holes tell us about the nature of time itself. Let me ask you something personal. Do you feel like time is flowing right now? Like there's a present moment, the now that you're experiencing, and it's continuously moving forward from past to future? Of course you do. We all do. It's one of the most basic features of conscious experience. But here's something that will rock your world. According to physics, this flow of time, this sense of a moving now, doesn't exist. It's an illusion, or at least, it's not a feature of the fundamental laws of physics. This realization comes directly from Einstein's theories of relativity, and it's most dramatically illustrated by what happens near black holes. Let's start with special relativity. Einstein showed that simultaneity, the concept of two events happening at the same time, is relative. It depends on your motion. If you're moving relative to me, events that are simultaneous for you are not simultaneous for me, and vice versa. This means there's no universal, now, no present moment that everyone agrees on. The universe doesn't have a single time. It has many times, depending on your reference frame. This already undermines the idea of time flowing, because if there's no universal present, what's doing the flowing? But general relativity makes it even more extreme. Near a black hole, time doesn't just depend on your motion. It depends on your position in the gravitational field. The closer you are to the event horizon, the slower time passes relative to someone far away. This is called gravitational time dilation, and it's been measured experimentally many times. In fact, GPS satellites have to correct for time dilation because they're farther from Earth's gravitational field than we are on the surface. Their clocks run slightly faster than ours, and if we didn't correct for this, GPS would be off by miles within hours. Now, imagine you're watching someone fall into a black hole. As they get closer to the event horizon, you see their time slow down relative to yours. Their movements become sluggish, their watch ticks slower, their speech draws out. Asymptotically, as they approach the horizon, time for them appears to stop completely from your perspective. You never actually see them cross the horizon. You see them frozen at the edge, their image getting dimmer and redder as time goes on, but never quite disappearing. From your perspective, they take infinite time to reach the horizon. But from their perspective, from the perspective of the infalling person, nothing special happens at the horizon. They cross it in a finite amount of their proper time, the time measured by their own watch. They probably wouldn't even notice the moment they crossed it, assuming the black hole is large enough that tidal forces haven't torn them apart yet. Their time continues normally. They keep thinking, breathing, existing, moving inexorably toward the singularity. So which perspective is correct? Do they cross the horizon or don't they? The answer is both. Both perspectives are equally valid. There is no absolute fact about when or whether the crossing happens, because there is no universal time. Time is local, personal, dependent on your path through spacetime. The infalling person crosses the horizon in their time. They never cross it in the external observer's time. Both statements are true simultaneously because simultaneously doesn't mean anything absolute. This has profound implications for the nature of time. If time is not universal, if different observers have different times, then time is not a single dimension along which the universe moves. Instead, time is more like a coordinate, a label we attach to events, and different observers use different coordinate systems. The past, present, and future don't have any absolute existence. They're just labels for different regions of spacetime. And which region you label as now depends on your motion and your position in spacetime. The physicist Brian Greene describes this using a concept called the block universe. Imagine spacetime as a four-dimensional block with 3 dimensions of space and 1 of time. The entire history of the universe, from the Big Bang to the far future, exists within this block. Your life is a world line, a path through the block. When you talk about now, you're talking about a particular 3-dimensional slice through this 4-dimensional block, a slice of constant time for you. But someone moving differently takes a different slice. Their now includes events in your past or future. The block itself doesn't change or flow, it just is. All moments exist equally, and the sense of time flowing, of the present moment moving through the block, is a feature of consciousness, not of the block itself. Black holes make this picture unavoidable. The relationship between the external observer, who never sees the horizon crossed, and the infalling observer who does cross it, it only makes sense if both the exterior and interior of the black hole exist simultaneously in the block universe. The infalling observer's future, including their crossing of the horizon and reaching the singularity, exists just as much as the external observer's present. Time doesn't flow spacetime, simply is. Now, if you're feeling a little existentially dizzy right now, good, you should be. This is one of the most profound implications of modern physics, and most people, even most physicists in their everyday thinking, don't fully internalize it. We're evolutionarily built to experience time as flowing, as having a special present moment, because that's useful for survival. But physics tells us this is a cognitive construction, not a feature of fundamental reality. But here's where it gets personal, where this connects to your life. If the block universe is correct, if all moments of time exist equally, then everything that has ever happened or will ever happen to you already exists in the spacetime block. Your birth, your death, every decision you've ever made or will make, they're all there, laid out in 4 dimensions. This raises deep questions about free will, about whether the future is determined, about what it means to make a choice. Some physicists and philosophers take this to mean that free will is an illusion. If the future already exists in the block universe, then it's already determined what you'll do, and your sense of choosing is just the experience of your consciousness moving along a predetermined world line. Others argue that the block universe is compatible with free will, because even though the future exists, it exists as a result of your choices. The world line you follow is determined by the decisions you make, and those decisions are real features of the space-time structure. You're not free to change your world line from outside of time, but you are free in the sense that your choices genuinely determine which world line is yours. This debate is ongoing, and I don't think physics alone can resolve it, because it touches on questions about consciousness and causation that go beyond physics. But what's undeniable is that black holes force us to confront these questions. They show us that time is not what our intuition tells us, and that our place in the universe, our experience of flowing through time, might be fundamentally different from what's really happening at the deepest level. Let me give you another angle on this. If time doesn't flow, if the block universe is correct, what explains the second law of thermodynamics? This is the law that says entropy, disorder, increases over time. It's why eggs break, but don't ungreek. Why coffee cools down, but doesn't spontaneously heat up. Why we age and die. The second law gives time a direction, an arrow pointing from past to future. But the fundamental laws of physics, including general relativity and quantum mechanics, are time-symmetric. They work just as well forward in time as backward. So where does the arrow of time come from? One answer, proposed by physicists like Roger Penrose, is that the arrow of time comes from the very low entropy state of the early universe at the Big Bang. The universe started in an incredibly special, low entropy configuration, and it's been increasing in entropy ever since, moving toward equilibrium. Our perception of time flowing from past to future is really our perception of entropy increasing, of the universe moving from order to disorder. And black holes play a crucial role in this story because they're the ultimate entropy sinks. They have enormous entropy encoded on their event horizons. As the universe ages, more and more matter falls into black holes. And if black holes evaporate via Hawking radiation, that entropy is released back into the universe. The final state of the universe in the far distant future might be a cold, dark expanse with nothing but evaporated black hole radiation, maximum entropy, heat death. But Penrose has proposed something even more radical, called conformal cyclic cosmology. He suggests that the heat death of the universe, when everything is smooth and featureless, is actually identical to the Big Bang of the next cosmic cycle. Time is cyclic, with each cycle beginning in a Big Bang and ending in heat death, which is the Big Bang of the next cycle. Black holes play a crucial role in this theory because they need to evaporate completely before the transition can happen. If this is correct, then time doesn't just flow at loops. This is speculative, but it illustrates how black holes are central to our deepest questions about time. They're not just exotic objects out there in space. They're laboratories for testing our understanding of temporality, causation, and the structure of reality. Now let me bring this back to something concrete. I said that black holes reveal time is not what you think it is. And I've shown you how they demonstrate that time is relative, that simultaneity is observer-dependent, that the flow of time might be an illusion. But there's one more aspect I need to mention, something that connects to quantum mechanics and makes the picture even more bizarre. In quantum mechanics, time plays a unique role. It's not an observable like position or momentum. You can't measure time itself. You measure the state of a system at a time. Time is the parameter that describes how quantum states evolve, but it's not part of the quantum state itself. This creates a problem when you try to combine quantum mechanics with general relativity, because in general relativity, time is part of the dynamical spacetime geometry. Time is curved along with space. So in quantum gravity, time should be quantized and subject to uncertainty, just like position and momentum. But if time is uncertain, what does it mean for a quantum state to evolve in time? This is called the problem of time, and it's one of the biggest challenges in quantum gravity. Different approaches handle it differently. In loop quantum gravity, some versions suggest that time might emerge from more fundamental quantum relationships between events. In the Wheeler-DeWitt equation, which is an attempt to write a quantum equation for the entire universe, time disappears entirely. The equation doesn't have a time variable at all. The universe is described by a timeless quantum state, and time emerges only as a correlation between different parts of the system. If this is correct, then at the deepest level, the universe is timeless. Time is not a fundamental feature of reality. It's an emergent phenomenon arising from quantum correlations, somewhat like how temperature emerges from molecular motion. Near black holes, where quantum effects and gravity are both strong, this timelessness might be detectable. The event horizon, which seems like a place in space where time goes weird, might actually be a window into the timeless quantum substrate of reality. This is heavy stuff, I know, but here's why it matters for you, personally. Your experience of time, your sense of the present moment, your memory of the past and anticipation of the future. These are some of the most fundamental aspects of consciousness. If physics tells us that time is not what it seems, this should change how you think about your life. It should make you question the narrative structure you impose on your existence, the sense that you're moving from past to present to future. Maybe you're not moving at all. Maybe all moments of your life exist simultaneously in the block universe. And consciousness is just the experience of being a particular pattern in spacetime. A pattern that includes memory and anticipation as internal structures, creating the illusion of motion. Or maybe time is real in some emergent sense, arising from quantum mechanics or thermodynamics, and the flow you experience is connected to real physical processes like entropy increase or the collapse of quantum wave functions. These are open questions, debated by physicists and philosophers, and they matter because they shape how we understand ourselves and our place in reality. Black holes, by pushing gravity and space-time to their extremes, force these questions into the open. They're not just out there in distant galaxies. They're mirrors reflecting back to us the deepest puzzles about existence. And the fact that you're here, watching this video, thinking about these ideas, is part of that cosmic story. Your consciousness, your ability to contemplate black holes and time and the nature of reality, is one of the universe's ways of understanding itself. Let me leave you with this thought as we transition to the next section. Every moment of your life, including right now, is carved into the structure of space-time. If the block universe is correct, then this moment, you reading or hearing these words, exists eternally as part of the four-dimensional geometry of reality. You're not just in the universe, you're a permanent part of its structure, a pattern in space-time that exists alongside black holes, stars, galaxies, and everything else. That should give you a sense of significance, of permanence, even in a cosmos where time might be an illusion. And as we continue, we're going to explore what this means for your worldview, for how you see yourself and your place in this strange, beautiful, terrifying universe. What if I told you that black holes might not be the end of information, but the beginning of something new? That the ultimate fate of everything that falls into a black hole might be rebirth in another universe? This is where we venture into truly speculative territory, but it's grounded in serious physics, and it's going to challenge your assumptions about destruction, creation, and the very concept of endings. Stay with me, because this next section explores one of the most mind-bending possibilities in cosmology, that black holes might be white holes, that information might tunnel through space-time, and that what looks like the end might actually be a doorway to something else entirely. Let's start with a simple question. What's on the other side of a black hole? General relativity, taken at face value, gives a surprising answer. The equations that describe black holes are perfectly symmetric in time. For every black hole solution, there's a corresponding white hole solution. A black hole is a region that you can enter but never escape. A white hole is a region that you can exit but never enter. Things can pour out of a white hole, but nothing can fall in. Time-reversed processes. Now, we've never observed a white hole, and most physicists think they don't exist because they would be incredibly unstable. Any small perturbation would cause them to collapse. But here's where it gets interesting. Some solutions to Einstein's equations, particularly the maximally extended Schwarzschild solution for a non-rotating black hole, describe a black hole and a white hole connected by a wormhole, with the black hole in one universe and the white hole in another. Matter that falls into the black hole could theoretically emerge from the white hole in another space-time. Now, before you get too excited, these solutions have a major problem. They are eternal. They exist for all time, unchanging. But real black holes form from collapsing stars, and the interior geometry is different from these eternal solutions. For a black hole formed from collapse, the connection to a white hole region probably doesn't exist, and in falling matter just hits the singularity and presumably ceases to exist in any recognizable form. And this is a big but quantum effects might change the picture completely. Remember loop quantum gravity and the idea of a Planck star? Some models suggest that when matter collapses inside a black hole, instead of forming a true singularity, it reaches a maximum density set by quantum gravity. At this point, quantum pressure could halt the collapse and even reverse it, creating a bounce. The matter rebounds outward, but because of extreme time dilation inside the black hole, this bounce takes an incredibly long time as seen from outside, potentially longer than the current age of the universe. In these models, a black hole eventually transitions into a white hole, explosively releasing the matter that fell in. From the outside, this would look like the black hole evaporating, but instead of gentle Hawking radiation, there would be a violent outburst at the end, a remnant of the original matter spewed back out. This is highly speculative, but it's based on serious attempts to extend general relativity into the quantum regime. Now, let me take this even further, into an idea proposed by Lee Smolin called cosmological natural selection. Smolin suggests that every black hole might create a new universe on the other side when matter collapses. To extreme densities inside a black hole, it might undergo something like a Big Bang, spawning a new expanding spacetime that is causally disconnected from ours. From our perspective, the matter disappears into the black hole and presumably hits a singularity. But from the perspective of that matter, perhaps it transitions into a new cosmic expansion, a new universe with its own physics, perhaps slightly different from ours. If this is correct, then black holes are not destroyers but creators. Every black hole is a universe factory. And our universe, in turn, might have been born from a black hole in a parent universe. This would mean the cosmos is not a single universe, but a vast multiverse, a tree of universes budding off from black holes, each with potentially different laws of physics determined by quantum fluctuations during the bounce. Smolin argues that this could explain fine-tuning. Our universe's physical constants seem precisely adjusted to allow for complexity, stars, planets, and life. Why? In cosmological natural selection, universes that produce more black holes have more offspring universes. And universes that produce lots of black holes need to have physics that allows for long-lived stars, which in turn creates the conditions for complexity and life. So the universe is fine-tuned for black holes, and we exist as a byproduct because black hole-producing universes also produce conditions suitable for life. It's natural selection applied to entire cosmos. This is speculative, and there's no direct evidence for it, but it's a testable idea in principle. If it's correct, and if the laws of physics in offspring universes are slightly mutated from their parent universes, then we could look for signatures of this in the structure of physics itself. Some physicists have tried to work out what changes to physical constants would maximize black hole production and see if our universe matches those predictions. The results are mixed, and the idea remains controversial. But I bring it up because it illustrates something profound. Black holes might not be the ultimate expression of destruction and ending, but rather points of transformation and creation. And this connects to a deeper philosophical point about the nature of information, existence, and what it means for something to end. Throughout this video, we've talked about information and entropy, about whether information is destroyed or preserved. But there's a sense in which this debate misses a larger truth. Information, at the quantum level, is not some abstract thing written down somewhere. It's the set of quantum correlations between different parts of the universe, the entanglement structure that relates one system to another. When something falls into a black hole, its quantum state becomes entangled with the black hole's quantum state. The information isn't destroyed, it's encoded in the relationships, the correlations, between the black hole and the rest of the universe. And here's where it gets deeply weird. From the perspective of quantum mechanics, the entire universe is described by a single quantum state, a wave function that encompasses everything. This wave function evolves in time according to the Schrödinger equation, and it never loses information. It's perfectly deterministic and reversible. But we don't experience the universe as a wave function. We experience it as a classical reality with definite outcomes. This is the measurement problem in quantum mechanics, and black holes make it especially acute. When you fall into a black hole, your quantum state becomes entangled with the black hole. From the perspective of someone outside, you're now part of the black hole's quantum state. But from your perspective, as you fall in, you continue to exist as a distinct entity until you reach the singularity. These two descriptions seem incompatible, and reconciling them requires understanding how quantum mechanics gives rise to classical experience, how the many possibilities in the wave function collapse into the single reality we observe. Some interpretations of quantum mechanics, like the many worlds interpretation, suggest that all possibilities are equally real, existing in parallel branches of the wave function. When you fall into a black hole, there are branches where you survive the journey to the singularity and branches where quantum fluctuations lead to different outcomes. All of these branches exist, and you split into multiple versions across them. In this view, black holes don't destroy information or possibilities, they just distribute them across many branches of reality. Other interpretations, like objective collapse theories, suggest that something physical happens when quantum states reach a certain threshold of complexity or mass, causing the wave function to collapse into a definite outcome. Some versions of these theories, particularly those developed by Roger Penrose, suggest that gravity itself causes wave function collapse. In this view, the extreme gravity near a black hole singularity would cause immediate collapse of any quantum superpositions, forcing reality to become definite. But this would have to happen in a way that preserves information globally, even if locally things seem to be destroyed. These are cutting-edge ideas, and we don't know which, if any, is correct. But they all point to something profound. Black holes are not just astrophysical objects. They're probes of the fundamental nature of reality, of quantum mechanics, of information, of what it means for something to exist. Every question we ask about black holes leads us deeper into the foundations of physics. And this brings me to the personal dimension of all this. You are made of information in a very real sense. Your body is a pattern of atoms, and those atoms are quantum systems in particular states. Your brain, your memories, your personality, they're all encoded in the specific arrangement and dynamics of neurons and molecules. Information is what makes you you. So when we ask whether information is preserved in black holes, we're asking whether anything that makes you could survive the most extreme conditions in the universe. And the answer, according to our best current understanding, is probably yes. Information is preserved. If you fell into a black hole, the information that constitutes you would become encoded in the black hole's quantum state and eventually re-emerge in Hawking, radiation, or in whatever mechanism preserves information. You wouldn't survive in any recognizable form. You'd be thoroughly scrambled and mixed with everything else. But the information would persist. In a very abstract sense, you can't be destroyed. You can only be transformed. This might seem like cold comfort after all. Being scrambled into Hawking radiation is not the same as living. But it speaks to a deeper point about identity and persistence. What are you, really? Are you the specific atoms that make up your body? Those atoms are constantly being replaced through metabolism. Are you the pattern, the information? That pattern is constantly changing as you learn, grow, and age. Are you the continuity of consciousness? But consciousness is interrupted every night when you sleep, and neuroscience suggests it's not even unified. It's more like a collection of processes that create the illusion of a single self. Black holes force us to confront these questions because they take the concepts of information, pattern, and persistence to their extremes. They show us that matter can be destroyed, atoms can be torn apart, but information, the abstract relationships that define structure, persists. And if you are fundamentally a pattern, a flow of information through spacetime, then in some sense, you're indestructible. You're a temporary arrangement of the universe. And when that arrangement dissolves, the components return to the cosmos to form new arrangements. You're not separate from the universe. You're one of the ways the universe arranges itself. And that arrangement is woven into the space-time fabric forever if the block universe is correct. This is both humbling and empowering. Humbling because it shows how transient and contingent your existence is. You're a fluctuation in the quantum field, a brief organization of matter and energy that will inevitably dissolve. But empowering because it shows that you're part of something larger, something that can't be destroyed. The information that is you will persist in some form, scattered and transformed, but never truly gone. You're a thread in the cosmic tapestry, and that thread extends through all of time. Now, I want to shift gears and talk about what all of this means for how you see yourself and your place in the universe. Because this isn't just abstract physics, it has implications for meaning, purpose, and how you live your life. We've been on a journey from a simple question about gravity and black holes to the deepest mysteries of space-time, information, and existence. And now we need to ask, so what? Why does this matter? How should this change the way you think about your life, your choices, and your relationship to the cosmos? That's what we're going to explore next, and it might be the most important part of this entire video. Welcome to the section where we get personal, where we take everything we've learned about black holes, gravity, space-time, and information, and we ask what it means for you. Not you in the abstract, but you, the person watching or listening to this right now, with your specific life, your worries, your dreams, your mortality. Because here's the truth. Physics is not just about equations and experiments. It's about understanding the nature of reality, and that includes your reality. So let's talk about what black holes teach us about being human. First, let's address the elephant in the room, nihilism. When you learn that time might be an illusion, that free will is questionable, that you're a temporary pattern of atoms that will dissolve, that the universe will eventually reach heat death where nothing meaningful can happen, it's easy to conclude that nothing matters. If we're just quantum fluctuations in a deterministic or many worlds universe, if consciousness is an epiphenomenon of information processing, if black holes will eventually swallow everything and evaporate, what's the point of anything? I want to push back hard against this conclusion because it's based on a category error. Meaning doesn't come from the universe being permanent or from you being cosmically significant in scale. Meaning comes from the relationships, the patterns, the experiences that make up your life. The fact that those patterns are temporary doesn't make them less real. The fact that you're small doesn't make your experience less valid. Think about it this way. Music is just vibrations in air. It's temporary, lasting only as long as the sound waves propagate. But does that make music meaningless? Does Beethoven's Ninth Symphony matter less because it's not eternal? Of course not. The meaning of music is in the experience of it, in how it makes you feel, in the patterns and structures that evoke emotion and thought. Your life is like that. It's a symphony in space-time, a pattern that has meaning precisely because it's structured, because it has complexity in relationships, not despite being temporary. Moreover, everything we've learned about black holes suggests that information is preserved, that patterns persist in some form even through the most extreme destruction. You are information. Your thoughts, your relationships, your impact on the world, these create correlations in the universe that persist. When you teach someone something, you've entangled your information with theirs. When you create art, you've encoded your patterns into physical media that others will interact with. When you show kindness to someone, you've changed their quantum state in ways that propagate forward. You're constantly writing yourself into the structure of space-time, and those writings don't disappear. They become part of the causal chain that shapes the future. Black holes teach us something profound about this. They show us that information is more fundamental than matter. Matter can be destroyed, atoms can be annihilated, but information, the abstract relationships and correlations, persists. You are more than your body. You are a pattern of information, and that pattern has an existence that transcends any particular physical instantiation. The specific atoms that make up your body right now are are not the same atoms that made up your body 7 years ago. You've been completely replaced, atom by atom, through metabolism. Yet you persist because the pattern persists. The information that is, you has continuity even as the substrate constantly changes. This should radically change how you think about death. Physical death is the dissolution of the pattern, the loss of the particular organization of matter that sustains your consciousness. It's real, and it's final in the sense that your subjective experience ends, but the information doesn't disappear. It spreads out into the environment, becomes part of other systems, influences other patterns. In a very real sense, you become part of everything else. Your atoms disperse and become part of other organisms, other processes. The information about you persists in the memories of people who knew you, in the things you created, in the causal effects you had on the world. And if the block universe is correct, then your entire life, every moment from birth to death, exists eternally as a structure in four-dimensional spacetime. You're not traveling through time toward oblivion. You're a fixed pattern in the geometry of reality, as permanent as any mathematical structure. From this perspective, death is not an end, but a boundary, like the edge of a painting. The painting doesn't cease to exist when it ends. It's complete. Your life in the block universe is a complete four-dimensional object, and it exists in its totality always. Now, I know some of you are thinking, this is all very abstract, but what does it mean for how I should live? Here's what I think. Understanding black holes and the nature of spacetime should make you more aware of the preciousness and contingency of your existence. You are a highly improbable configuration of matter and energy. The odds against you existing are astronomical, and it should inspire urgency. If you're a temporary pattern, then your time is limited. The block universe might suggest that all moments exist equally, but you only experience them once, in sequence. Every moment that passes is a moment you can't get back, not because it's destroyed, but because your consciousness moves forward, and you can only experience the present. This isn't cause for despair. It's cause for engagement. It means that what you do matters, not in some cosmic eternal sense, but in the sense that it shapes the pattern that is you, and that pattern is unique and irreplaceable. Let me give you something practical. Knowing about black holes and the fundamental nature of reality should change three things about how you live. First, it should make you less afraid of failure and embarrassment. From a cosmic perspective, your mistakes are infinitesimally small. They don't matter to the universe. The only place they matter is in your own pattern, in your own experience, and in the experiences of people immediately around you. So take risks, try things, fail spectacularly. Your failures are part of the complexity that makes your pattern interesting. A life without variation, without mistakes, without unexpected turns, is a boring pattern. Complexity and beauty come from variation and error, from the unexpected. Black holes form because of irregularities in matter distribution. Stars form because of quantum fluctuations. Life evolves because of copying errors. Your failures are features, not bugs. Second, it should make you more compassionate. Every person you meet is also a temporary pattern, a unique configuration that has never existed before and will never exist again. They're fighting to maintain their pattern against entropy, against the dissolution that awaits all of us. They're experiencing the same confusion about existence that you are. They're asking the same questions about meaning and purpose. When you understand that we're all patterns in space-time, all information structures trying to persist and understand ourselves, it becomes harder to dehumanize people, harder to see them as obstacles or enemies. We're all in this together, all part of the same quantum wave function, all connected through the web of causation that constitutes space-time. Third, it should make you more focused on experience over accumulation. If you're information, then what matters is not what you have, but your process, what patterns you create in your own consciousness and in the world. Experiences create information. Learning creates information. Relationships create information. Art creates information. Accumulating stuff doesn't create much information. It's mostly redundant. $1 million in the bank is just a number in a computer, a simple piece of information. But a conversation with someone you love, a moment of insight, a beautiful sunset, these are complex patterns that enrich the information structure that is you. Black holes destroy matter, but preserve information. They teach us that what's fundamental is not the stuff, but the relationships, the correlations, the patterns. You should live accordingly. Seek experiences that create complexity in your consciousness. Seek relationships that create entanglement with other minds. Seek learning that creates new patterns in your understanding. These are the things that enrich the four-dimensional sculpture that is your life in space-time. Now, let's talk about something even more personal, your sense of self. Throughout this video, we've been talking about you as if you're a single, unified thing. But are you? Neuroscience suggests that consciousness is not unified. It's a collection of processes that create the illusion of a single experiencer. Your brain has different modules that process different things: vision, language, emotion, memory, and these modules don't always agree. The self is more like a democratic government than a monarch, and sometimes the different factions are in conflict. Black holes and quantum mechanics reinforce this picture. If you're made of quantum particles in superposition, then at the deepest level, you're not in a single definite state. You're spread out over many possibilities, and it's only through decoherence interaction with the environment that you appear to have definite properties. In the many worlds interpretation, every quantum measurement splits you into multiple versions in different branches. Right now, as you watch this video, countless versions of you are branching off, making slightly different decisions, having slightly different thoughts. This might seem disturbing. Am I not even a single coherent entity? But I think it's actually liberating. It means you're not trapped by your past. The self you were yesterday is not the self you are today. The pattern is always changing, always evolving. You have the freedom to reshape yourself, to create new patterns, to become something different. The idea of a fixed, essential self is an illusion. You're a process, not a thing. You're a verb, not a noun. You're something the universe is doing right now, and what you're doing can change. Black holes teach us about transformation. Matter falls in as one thing and comes out as something completely different: random thermal radiation. It's destroyed and recreated. You undergo similar transformations throughout your life. The you that you were as a child is gone, destroyed, transformed into the you that exists now. And the you that exists now will be destroyed and transformed into the you of the future. This is not death. It's life. It's the dynamic, ever-changing nature of existing in time. And here's something that should blow your mind one last time. Your consciousness might extend beyond your brain. If consciousness is related to information processing, and if information is fundamentally about correlations and relationships, then your consciousness might be partially located in the environment, in the people you interact with, in the tools you use, in the culture you participate in. This idea, called extended cognition, suggests that your smartphone is literally part of your mind. Your memory is distributed across your brain, your notes, your devices. Your decision-making involves not just your neurons, but conversations with other people, books you've read, cultural norms you've internalized. In this view, you're not an isolated island of consciousness in a skull. You're a network, extended through space and connected to other networks. And when you die, parts of that network persist. The people who knew you carry your patterns. The culture you contributed to carries your information. You're diffused throughout the social and informational structure of humanity, and that structure will persist long after your biological body ceases to function. Black holes and quantum mechanics suggest something similar at a physical level. You're not a separate object in the universe. You're a highly entangled subsystem of the universal quantum state. The boundaries between you and the environment are fuzzy and somewhat arbitrary. Where exactly do you end and the external world begin? At your skin? At the air you're breathing? At the light entering your eyes? At the electromagnetic fields produced by your neurons? The answer is that there is no sharp boundary. You fade out gradually into the environment, and the environment extends into you. This should change how you think about your relationship with the world. You're not separate from nature, observing it from outside. You're a particularly complex and self-aware part of nature, observing itself. When you look at a tree, atoms that were once in trees are now in you, and atoms that are now in you will someday be in trees. You're constantly exchanging matter and energy with the environment. You're a temporary eddy in the flow of matter and energy through space-time, a whirlpool that maintains its pattern for a while and then dissipates, but the water keeps flowing. And this brings me to perhaps the most important point of this entire video. You are not insignificant. I know that learning about the vastness of space, the violence of black holes, the ultimate heat death of the universe, can make you feel small and meaningless. But significance is not about size or duration. It's about complexity, about the richness of patterns and relationships. You are the most complex thing we know of in the universe. Your brain has roughly 86 billion neurons, each connected to thousands of others, creating a network with something like 100 trillion synapses. The number of possible states your brain can be in is larger than the number of atoms in the observable universe. The complexity of your consciousness, the depth of your experiences, the richness of your inner life, these exceed anything else we've discovered in the cosmos. Yes, black holes are powerful. They can trap light and bend space-time, but they're simple. A black hole is characterized by just a few numbers: mass, spin, and charge. That's it. All the complexity of the matter that fell in gets erased, reduced to these simple parameters. You, on the other hand, cannot be reduced. You are irreducibly complex. Your thoughts, your emotions, your memories, your relationships, they form a pattern so intricate that it would take more information to describe you completely than is contained in a black hole millions of times more massive than the sun. So when you feel insignificant, remember this. Significance is not measured in kilograms or light years. It's measured in complexity and experience. You are a marvel. You are a pinnacle of organization in a universe that tends toward disorder. You are a pocket of awareness in a cosmos that is mostly empty space and radiation. You are one of the ways the universe has become conscious of itself, and that is profoundly significant. Moreover, you have agency. You can make choices that affect the pattern that is you and the patterns around you. You can create beauty, foster connections, generate new ideas, help others. These acts don't change the ultimate fate of the universe. Heat death is still coming in 10 to the power of 100 years or so. But they change the structure of space-time between now and then. They create information, complexity, meaning. And if the block universe is correct, those changes are eternal. The kindness you show, the art you create, the love you give, these are woven into the four-dimensional fabric of space-time forever. Black holes teach us that the universe is stranger and more wonderful than we imagined. They teach us that space and time are not what they seem, that information is fundamental, that destruction might be transformation. But most importantly, they teach us humility and wonder humility about our place in the cosmos, and wonder at the fact that we exist at all, that we can understand even a little bit about how reality works. You are stardust that learned to think. You are a pattern of information that emerged from quantum fluctuations in the early universe, that evolved over billions of years. It became conscious and self-aware. You are the universe experiencing itself, knowing itself, asking questions about itself. And for a brief moment in cosmic time, you get to be part of this grand adventure of existence. So what should you do with this knowledge? Live fully. Love deeply. Think boldly. Create beauty. Seek truth. Be kind. Not because there's some cosmic meaning imposed from outside, but because these are the things that create richness and complexity in the pattern that is you. These are the things that make your brief existence meaningful. And when you look up at the night sky and think about black holes out there, warping space-time, preserving information, teaching us about the nature of reality, remember that you're connected to them. The atoms in your body were forged in stars that might have ended as black holes. The physical laws that govern black holes also govern you. You're made of the same quantum fields, subject to the same space-time geometry. You're not separate from the cosmos. You're a part of it, and understanding black holes is understanding. In your life, you should do the same. Make decisions based on the best information you have, but hold your beliefs probabilistically. Don't be dogmatic. Don't require absolute certainty before committing to something. That's a recipe for paralysis. But also don't ignore evidence that challenges your beliefs. Be willing to update, to change your mind, to admit when you were wrong. Black holes teach us another important lesson about uncertainty: the value of thought experiments and limiting cases. When we can't directly observe something like the interior of a black hole or the behavior of quantum fields in extreme gravity, we can still make progress by thinking carefully about limiting cases, by seeing what our theories predict in idealized situations, by looking for logical inconsistencies or paradoxes. The information paradox, the firewall problem, the black hole complementarity proposal, these all came from thought experiments, from physicists sitting and thinking carefully about what quantum mechanics and general relativity imply when pushed to their limits. And these thought experiments have driven real progress, suggesting new directions for research, new experiments to perform, new mathematical structures to explore. You can use the same approach in your life. When you're uncertain about something important, don't just give up and say, "I can't know." Instead, think through the implications of different possibilities. What would your life look like if choice A is correct versus choice B? What evidence would help you distinguish between them? What are the limiting cases, the extreme scenarios that might clarify the underlying principles? For example, if you're deciding whether to pursue a particular career, don't just worry about the uncertainty. Think through the scenarios. What's the best case? What's the worst case? What's most likely? What would you do if the worst case happened? What skills would you develop? What doors would open or close? This kind of analysis doesn't eliminate uncertainty, but it transforms it from paralyzing anxiety into structured decision-making. Black holes also teach us about the importance of multiple perspectives. We've seen throughout this video that black holes look different depending on your frame of reference. An infalling observer crosses the horizon smoothly. An external observer never sees the crossing. Both perspectives are valid, and the full picture requires understanding both. This is true in life as well. Your perspective on a situation is valid, but so are other people's perspectives. The full truth often requires integrating multiple viewpoints, even when they seem contradictory. Your subjective experience is real. You're the authority on what it feels like to be you. But other people's descriptions of you also capture real aspects of who you are. The self you experience from inside is different from the self others observe from outside, and both are real. This should make you more intellectually humble and more curious about other perspectives. When someone disagrees with you, instead of immediately assuming they're wrong, consider that they might be observing a different aspect of reality, a different frame of reference. The truth might be larger than either of your perspectives and might require integrating both. Let me tell you about one more thing that black holes teach us about uncertainty: the value of approximations. General relativity is an approximation. It's wrong at the Planck scale. Quantum mechanics is an approximation. It doesn't include gravity. And yet, these approximate theories are useful. They work brilliantly in their respective domains. When we eventually develop a theory of quantum gravity, it will probably reduce to general relativity in the classical limit and to quantum mechanics in the weak gravity limit. This is how science progresses. We don't start with the complete final truth. We start with approximations that work in limited domains, and we gradually expand and refine them. Newton's gravity was an approximation. Einstein's gravity is a better approximation. Quantum gravity will be an even better approximation, but it might still be an approximation of something even deeper. In your life, you should embrace this approach. Don't wait for perfect knowledge before acting. Use approximations. Use rules of thumb. Use heuristics. They won't always be right, but if they're right most of the time, they're useful. And as you gain experience, you'll refine them, developing better approximations, more nuanced understanding. For example, early in your career, you might use simple heuristics like work hard and good things will happen, or networking is important. These are approximations. They're not always true, but they're useful starting points. As you gain experience, you'll develop more sophisticated models of how your field works, what strategies are effective, what pitfalls to avoid. You're doing science on your own life, constantly testing hypotheses and updating your models. Black holes also teach us about the value of mathematical thinking, even when we're uncertain about physical reality. The mathematics of black holes is well defined. We can calculate precisely what general relativity predicts, even if we're not sure whether those predictions apply in the real world at the Planck scale. The math gives us a framework for thinking, for exploring possibilities, for making connections between different ideas. You can use mathematical thinking in your life, even if you're not dealing with equations. Mathematical thinking is really just precise, logical thinking. It's about defining terms clearly, making explicit assumptions, following logical chains of reasoning, checking for consistency. When you're uncertain about something, try to formalize it a bit. Write down your assumptions. Spell out the logical connections. See if your reasoning holds together. For instance, if you're anxious about money, don't just worry vaguely. Do the math. Calculate your expenses. Project your income. See what the numbers actually say. Often, you'll find that the situation is either better than you feared or worse than you thought. But either way, having concrete numbers gives you something to work with. Uncertainty becomes quantified risk, which you can then address systematically. Now, let me address something that might be bothering some of you. Throughout this video, I've presented speculative ideas, white holes, cosmological natural selection, many worlds, the holographic principle alongside more established physics. Some of you might feel like I've been presenting guesses as facts, or like I haven't been clear enough about what's established versus what's speculative. Here's the thing, that ambiguity is intentional, to a degree. I want you to develop a feel for the frontier of knowledge, for what it's like to be at the edge where we're not sure what's true yet. This is where the exciting work happens. This is where new discoveries are made. And learning to navigate this space, where some ideas are well established, some are plausible but unproven, and some are wild speculations, is a crucial skill. In the real world, you're rarely dealing with absolute certainty. You're usually operating at the frontier of your own knowledge, making decisions with incomplete information, navigating between established facts and educated guesses. Learning physics trains you for this. It shows you how to reason under uncertainty, how to distinguish between different levels of confidence, how to make progress despite not having all the answers. So let me give you a framework for thinking about different levels of certainty in physics, which you can then apply to other domains. Level 1, well-established facts. These have been tested extensively and are confirmed by multiple independent experiments. Examples: general relativity accurately describes gravity in most situations. Quantum mechanics correctly predicts atomic behavior. Black holes exist. You should accept these with high confidence, though always with the understanding that they might be approximations of something deeper. Level 2. Strong theoretical predictions that haven't been fully tested. These follow from well-established theories and are considered likely to be true, but haven't been comprehensively verified. Examples: Hawking radiation exists. Information is preserved in black holes. Gravitational waves exist. This was level 2 until 2015. Now it's level 1. You should take these seriously and expect them to be confirmed, but remain open to surprises. Level 3. Speculative but plausible ideas. These are consistent with known physics and solve some problems, but require assumptions that haven't been tested. Examples: the holographic principle, black hole complementarity, loop quantum gravity's Planck stars. You should understand these as possibilities, not facts. They're worth thinking about and exploring, but don't bet your life on them. Level 4. Wild speculations. These are interesting ideas that might be true, but require major assumptions or extensions to known physics. Examples: cosmological natural selection, consciousness collapses wave functions, A equals EPR connects all entangled particles. Treat these as thought experiments, as ways of exploring possibility space. They're fun to think about, but don't confuse them with established science. In your own life, learn to categorize your beliefs this way. Some things you know with high confidence: your name, your relationships, your skills. Some things you believe based on strong evidence, but haven't fully verified. Your understanding of how your field works, your models of other people's motivations. Some things are plausible, but uncertain: your predictions about future events, your guesses about what career path will satisfy you. And some things are wild speculations, your hopes for how technology might develop, your theories about the meaning of life. Hold each level appropriately. Don't cling too tightly to speculations as if they were facts. But also don't dismiss established facts just because you don't like their implications. And most importantly, stay curious about the middle levels where the interesting questions live. Black holes exist at that middle level in many ways. We know they exist, level 1. We're pretty sure they emit Hawking radiation, level 2. We think information is probably preserved, maybe through holographic encoding, level 3. We wonder if they might create new universes or connect to white holes, level 4. Navigating these different levels, holding them all in mind simultaneously while giving each appropriate weight, is the art of thinking about cutting-edge physics. And here's the beautiful thing: uncertainty doesn't mean ignorance. We know an enormous amount about black holes, despite the many open questions. We can calculate their properties, predict their behavior, detect them with gravitational waves, observe matter falling into them. The existence of unanswered questions doesn't invalidate what we do know. It just means there's more to discover. This is true in your life as well. You can know a lot about yourself, your values, your strengths, your relationships, even while being uncertain about the future, about the best choices to make, about the ultimate meaning of your existence. Knowledge and uncertainty coexist. They're not opposites. They're complementary aspects of engaged, honest thinking. So here's my challenge to you: embrace uncertainty. Don't see it as a problem to be solved or an obstacle to overcome. See it as the natural state of any mind that's pushing at the boundaries of understanding. If you're certain about everything, you're not thinking hard enough. If you're uncertain about everything, you're not learning. The sweet spot is in the middle, confident in some things, uncertain about others. Always learning, always updating, always pushing forward. Black holes teach us this lesson viscerally. They're objects of certainty. We've observed them, measured them, confirmed their existence. But they're also objects of deep mystery. We don't understand their quantum properties, their information processing, their ultimate fate. And that combination of knowledge and mystery is what makes them so fascinating, so productive for research, so rich with possibilities. Your life should have the same quality. Know some things deeply. Be uncertain about others. Stay curious. keep learning. Don't be afraid to be wrong. Don't be afraid to change your mind. The greatest physicists in history, Einstein, Hawking, Bohr, Feynman, all made mistakes, changed their views, struggled with uncertainty. That's not a bug, it's a feature. That's how progress happens. And remember, the goal is not to eliminate uncertainty. The goal is to live well despite it, to make good decisions despite incomplete information, to find meaning despite not having all the answers. Black holes show us that even in the most extreme conditions, in the most uncertain domains, we can still make progress, still understand something, still find patterns and beauty and truth. So as we approach the end of this video, I want you to sit with that uncertainty. You've learned a lot, but you also have more questions now than when you started. That's perfect. That's exactly how it should be. Good education doesn't give you all the answers. It teaches you how to ask better questions, how to think more clearly, how to be comfortable in the space of not knowing while still moving forward. And now, in our final section, I want to bring everything together. We've covered gravity, space-time, quantum mechanics, information, time, identity, meaning, and uncertainty. All of these threads weave together into a larger picture, a vision of reality that's both humbling and empowering, both strange and beautiful. We're going to pull back and see the whole tapestry, and I'm going to leave you with a vision of what it means to be human in a universe of black holes, quantum mechanics, and curved spacetime. This is where everything clicks into place. We've been on quite a journey, haven't we? We started with a simple question. If light can't escape a black hole, why can gravity? And we've traveled through curved spacetime, quantum mechanics, information theory, the nature of time, consciousness, meaning, and uncertainty. Now, in these final minutes, I want to tie it all together and show you how all of these pieces form a single, coherent picture, a new way of understanding your place in this strange, magnificent universe. Here's the core insight that unifies everything we've discussed. Reality is fundamentally about information and relationships, not about things. This is the lesson that emerges when you take black holes seriously, when you push physics to its limits, when you try to reconcile quantum mechanics with gravity. The universe is not made of particles or fields or spacetime as fundamental ingredients. Those are useful descriptions, effective theories that work at certain scales. But at the deepest level, reality is made of information, quantum information. To be precise, and the structure of reality is determined by how that information is correlated and entangled. Think about what we've learned. Black holes preserve information, not matter. The entropy of a black hole, its information content, is proportional to its surface area, suggesting that three-dimensional space might be a holographic projection of two-dimensional information. Quantum entanglement, the correlations between particles, might literally be what space is made of Einstein-Rosen bridges connecting entangled particles. Time might emerge from quantum correlations and entropy increase, not exist fundamentally. Your consciousness, yourself, is better understood as a pattern of information than as a thing that exists in a particular place. All of these point to the same conclusion. Information is fundamental, and everything else, matter, energy, space, time, emerges from it. This is called the it from bit hypothesis, popularized by physicist John Wheeler. Every physical thing comes from bit binary information, the fundamental quantum choice between yes and no, 0 and 1, spin up and spin down. If this is correct, and the evidence is mounting that it is, then you need to completely rethink what you are. You are not primarily a physical body. You are a pattern of information that happens to be instantiated in physical matter. The atoms in your body are just the substrate, the medium. What makes you you is the pattern, the information, the specific relationships and correlations between different parts of your system. This has profound implications. First, it means you're constantly being recreated. The pattern that is you is maintained, Not by keeping the same atoms, those are constantly being replaced, but by maintaining the same informational structure. Every moment, you're bootstrapping yourself back into existence, maintaining the pattern against entropy, against the universe's tendency toward disorder. You're a flame, not a rock. A flame is a process, not a thing. It's a pattern of chemical reactions that maintains itself by consuming fuel and releasing heat. The specific molecules in the flame are constantly changing, but the flame persists as long as the process continues. You're the same. You're not a static object. You're a dynamic process, a self-maintaining pattern of information flow. Second, it means your boundaries are not as clear as you think. Information doesn't respect spatial boundaries. Your memories are partly in your brain, partly encoded in your environment, in photos, in places you've been, in other people's brains. Your decision-making process extends beyond your skull to include tools, social networks, cultural knowledge. Where exactly does you end and not you begin? The answer is fuzzy and context-dependent. You're more like a cloud than a marble. You have a dense center, but you fade out gradually with no sharp boundary. Third, it means you're deeply connected to everything else. If spacetime is built from quantum entanglement, then at the deepest level, you're entangled with the rest of the universe. Not in some vague, mystical sense, but in a precise, physical sense. The quantum fields that make up your body are the same fields that make up everything else. You're a localized excitation in these fields, but the fields are universal. You're a wave in the ocean, and the ocean is all of spacetime. You're not separate from the universe. You're a particularly complex and self-aware part of it. Now, let's connect this back to black holes one final time. Black holes are the universe's ultimate information processors. They take in complex matter stars, planets, everything, and encode all that information on their event horizons. They're the universe's way of compressing information, of taking three-dimensional complexity and projecting it onto a two-dimensional surface. And in doing so, they reveal the holographic nature of reality itself. When you understand this, black holes stop being just exotic astronomical objects and become metaphors for existence itself. You are also an information processor. You take in sensory data, memories, experiences, and you compress them, encode them, create representations. Your consciousness is the universe processing information about itself. Every thought you have, every perception, every memory is the universe computing, is information being transformed and reorganized. And just as black holes ultimately evaporate, returning their information to the universe in scrambled form through Hawking radiation, you too will eventually dissolve. Your pattern will break down. The information, that is, you will be released back into the environment, scattered and transformed, but never destroyed. You will become part of other systems, other patterns. The atoms that are currently organized as you will be reorganized into soil, into plants, into other organisms. The information and causal effects you had on the world will propagate forward, influencing future events in ways you can't predict. This is not death in the sense of annihilation. It's transformation. It's returning to the source. The pattern that is you is temporary, but the information persists. The causal chain continues. The universe goes on computing. You are one frame in an infinite movie, one configuration in an endless sequence of transformations. And here's what makes this empowering rather than depressing. You get to choose what information you create, what patterns you instantiate, what mark you leave on the fabric of spacetime. Every choice you make literally shapes the structure of reality, not in some metaphorical sense, but physically. Your choices determine which quantum states are realized, which correlations are established, which information structures emerge. When you help someone, you're creating new information, new correlations between your pattern and theirs. When you learn something, you're reorganizing the information structure of your consciousness. When you create art, you're encoding information in physical form that will persist and influence others. When you love someone, you're establishing deep entanglement between your quantum states. You're literally becoming connected at a physical level. These acts matter, not because there's a cosmic scoreboard, not because you'll be rewarded in an afterlife, but because they shape the structure of reality itself. The universe is computing, and you are part of that computation. Your choices are inputs that affect outputs. The patterns you create ripple forward through causation, influencing everything that comes after. Black holes teach us that information is conserved, that patterns persist even through the most extreme destruction. This should give you a sense of permanence and significance. Everything you do is written into the structure of spacetime. In the block universe, your entire life exists as a four-dimensional sculpture. The kindness you showed yesterday exists as much as the Big Bang or the heat death of the universe. It's all equally real, all part of the same space-time geometry. This means your life has inherent meaning, not assigned from outside, but emerging from the patterns you create. Meaning is not something you find. It's something you generate through the complexity and beauty of the information structures you instantiate. A meaningful life is one that creates rich patterns, deep connections, complex information. It's a life lived with intention, with awareness, with engagement. And here's the ultimate lesson, the synthesis of everything we've discussed. You are the universe experiencing itself. This is not a metaphor. You are literally made of the universe, same atoms, same quantum fields, same spacetime. And you have the extraordinary ability to reflect on your own existence, to contemplate black holes and infinity and the nature of reality. You are matter that has become conscious, information that has become self-aware, the universe that has learned to ask questions about itself. This is staggeringly improbable and precious. In most of the universe, in the vast empty spaces between galaxies, in the depths of stars, in the interiors of black holes, there is no consciousness, no awareness, no reflection. Just physical processes playing out according to mathematical laws. But here, in this tiny pocket of spacetime, on this small planet orbiting an ordinary star, matter has organized itself into patterns capable of thought, of emotion, of understanding. You represent billions of years of cosmic evolution. The hydrogen in your body was created in the Big Bang. The heavier elements were forged in stars and supernova explosions. The molecules that make up your cells were assembled through billions of years of chemical and biological evolution. Your consciousness is the culmination of this entire process. You are the universe's attempt to understand itself, and that is profound beyond measure. So when you look up at the night sky and see stars, remember that you are looking at your own past. Those photons traveled for years or centuries to reach your eyes, carrying information about distant places and times. When you contemplate black holes, remember that you are contemplating the most extreme physical conditions in reality, the places where our understanding breaks down and new physics emerges. And when you think about yourself, remember that you are not separate from any of this. You are woven into the same fabric. You are made of stars. You are a part of spacetime. You are the universe. This should fill you with wonder, with gratitude, with a sense of connection to everything that exists. It should make you want to live fully, to experience deeply, to understand broadly, to connect authentically. Because you are part of something vast and ancient and ongoing. And your brief moment of consciousness is a gift not given by anyone, but emergent from the structure of reality itself. And it should make you curious. There is so much we don't know. We don't have quantum gravity. We don't understand consciousness. We don't know if there are other universes or other dimensions. We don't know if life exists elsewhere in the cosmos. We don't know what new physics might be discovered in the next century or millennium. The story of understanding is far from over. We're in the middle chapters, still learning, still discovering, still being surprised by reality. You are part of that ongoing story of discovery. Every time you learn something new, Every time you have an insight, every time you make a connection between ideas, you are participating in the universe's self-exploration. You are one of the ways reality investigates itself. And while your individual contribution might be small, you probably won't discover the theory of quantum gravity or prove the holographic principle. It matters that you engage, that you think, that you wonder. Because here's the thing about information. It compounds. Every person who understands something can teach others. Knowledge spreads, builds on itself, creates new possibilities. Your understanding of black holes and space-time, limited as it might be, is still remarkable. You now know things that the smartest people in human history, Aristotle, Newton, even Einstein for most of his life, didn't know. You understand that space-time is curved, that quantum mechanics is probabilistic, that information is fundamental. This knowledge took thousands of years of collective human effort to develop. And now you have it. You can share it, build on it, use it to think about new problems. This is the power of being human in the 21st century. You have access to more knowledge than has ever been available before. The entire accumulated wisdom of our species is at your fingertips. You can learn about black holes, quantum mechanics, ancient history, molecular biology, philosophy, art, music, anything that interests you. You can connect ideas from different domains, see patterns that others haven't noticed, contribute to the collective understanding. And even if you never make a major scientific discovery, even if you never solve a cosmic mystery, your life still contributes to the overall computation that is the universe. Your experiences, your relationships, your choices, they all create information, complexity, structure. They all matter in the literal sense of affecting the matter and energy around you. So here's what I want you to take away from this entire video. You are significant. Not because you're large or permanent, but because you're complex and aware. You are temporary, but the information that is, you persists in transformed ways. You are small, but you're part of something vast. You are uncertain about many things, but you can still make progress, still understand, still create meaning. You are connected to everything, to stars, to black holes, to every other conscious being, to the structure of space-time itself. And the question, why can gravity escape from a black hole if light cannot, leads you to all of this. It leads you to understanding that gravity is not a force, but the curvature of space-time. That space-time is not a passive background, but a dynamic entity. That quantum mechanics and gravity need to be unified. That information is fundamental. That time might be an illusion. That you are a pattern in space-time, not a thing occupying space. That your existence is improbable and precious. That you are the universe experiencing itself. This is why physics matters. Not just for building technology or making predictions, but for understanding who and what you are. Physics is philosophy made precise. It's the deepest investigation into the nature of reality that our species has undertaken. And when you engage with it, when you think about black holes and space-time and quantum mechanics, you're participating in humanity's grandest project, understanding existence itself. So keep wondering, keep questioning, keep learning. Stay curious about black holes and space-time and all the other mysteries of the cosmos. But also stay curious about yourself, about consciousness, about meaning, about how to live well in a strange universe. These are all related questions. They're all part of the same investigation into what is real and what matters. And remember, every person who thinks deeply about these questions contributes to our collective understanding. You don't need to be a professional physicist to engage with these ideas. You don't need advanced mathematics to wonder about the nature of time or the significance of your existence. You just need curiosity, intellectual honesty, and the willingness to sit with uncertainty while still seeking clarity. Black holes are out there in the cosmos, warping space-time, storing information, teaching us about the limits of our understanding. But they're also in here, in your mind, in your attempt to comprehend them. The black hole in your thoughts is as real as the black hole in space. Both are patterns of information. Both are part of the universe's structure. Both matter. Thank you for taking this journey with me. Thank you for spending these hours thinking about gravity, black holes, space-time, information, consciousness, and meaning. You could have been doing anything else, but you chose to explore these ideas, and that choice matters. You've created new information structures in your consciousness. You've established new connections between concepts. You've participated in the universe's ongoing computation. Before you go, hit that subscribe button if you haven't already. Leave a comment telling me what blew your mind the most, what you're still confused about, what you want to explore next. And share this video with someone who you think would appreciate it. Knowledge compounds when it's shared. Understanding deepens through discussion. The more people thinking about these ideas, the richer our collective exploration becomes. And here's my final challenge to you. Take one idea from this video, just one thing that resonated with you, and let it change how you live this week. Maybe it's the idea that information is fundamental, so you'll focus on creating meaningful experiences rather than accumulating stuff. Maybe it's the idea that time might be an illusion, so you'll be more present in each moment. Maybe it's the idea that you're connected to everything, so you'll treat others with more compassion. Maybe it's the idea that uncertainty is not a problem, but a natural state, so you'll be more comfortable taking risks. Whatever it is, let this knowledge move from your head to your life. Let it become part of your pattern, part of the information structure that is you. Because that's when understanding becomes wisdom. That's when physics becomes philosophy. That's when information transforms into meaning. You are stardust that learned to think. You are the universe contemplating itself. You are a temporary pattern in an eternal fabric. You are small and vast, mortal, and connected to infinity, uncertain and capable of understanding. You are a human in a cosmos of black holes and curved space-time and quantum entanglement. You are here, now, aware, thinking, feeling, being. And that is extraordinary. Thank you for watching. Keep exploring, keep wondering, keep being amazed by this strange, beautiful universe we find ourselves in. Until next time, stay curious.